Important subspaces. This part is from section 4.2 and 2.8. In the last lecture, we talked about the definition of vector space. In this part, we're going to introduce two important vector spaces. Those are column space and null space. We first look at subspace. What is subspace? It is a vector space, but from another larger vector space. And we're often asked the question, so suppose V is a vector space, and A is some subset of V. Is A a subspace? Which means you want to check all conditions of vector space for this A. And we know that there are like 10 rules in the definition of vector space. But for subspace, because this is already from vector space, we don't need to check one by one or go through all 10 conditions. Only 3 conditions we need to go through are given here. So to check a subset of a vector space, it's enough to check, is 0 in a subset? Is it closed under addition? Is it closed under scalar multiplication? Let's look at one example. A subset of V is given by span of V1, V2, Vp. Is it subspace? The answer is yes. So to prove that, we need to check 3 conditions. So is 0 in, suppose for simplicity, I will write this span as A, span of V1, V2, Vp as A. So is 0 in A? Yes, because 0 is 0 times V1, 0 times V2, 0 times Vp. So we recall that span of V1, V2, Vp is the collection of all vectors given by linear combination of these P many vectors. So we have those weights for each bit in front of each given vectors. In other words, this is linear combination. Now, second question, is it closed under addition? The answer is also yes, because if you're given 2 vectors from A, then you can always write that these 2 vectors as linear combination. Suppose these 2, so for any 2 vectors from A, in A, we can always write V as linear combination. Suppose this linear combination is A1, V1, A2, V2, AN, Vp. And W is also from A. In other words, this can be written as linear combination, but probably with different coefficients. Then if you add them up, V plus W, the only question is it still in A? So simple calculation is that by combining like terms, this can be written as A1 plus B1, V1. So this becomes weight for V1, and A2, B2, V2. AP plus BP, VP. So this is again a linear combination. In other words, this is in A. So it is closed under addition. Now the last question is it closed under multiplication, scalar multiplication. The answer is also yes, because for any v in A, we can write that as A1, V1, so linear combination of these vectors. And if you multiply by C, any scalar to V, then this can be again write CA1, V1, and CAP, VP. So those are coefficients or weights for this linear combination. That means this is in A. So we're done. Column space. What is column space? The definition is following. The column space of matrix A is a subspace spanned by the columns of A, denoted by column of A. So we have, like, suppose A is a matrix, so n by n, then there are 1 column, 2 column, 3 column, all the way to the end. So we can write this as the first column we denote by A1, A2, all the way AN. Then what is column space of A? Column space of A is actually span of those A1, A2, AN. And this is subspace because we already proved span of some vectors gives a subspace. Now, typical question is for matrix A, we will ask, is a vector V belongs to this column A? To check this question, we need to go through these two steps. So we can rewrite the question again. So is V in column space of A? Then this is equivalent to say, is V a linear combination of A1, A2, AN? So we can write it, if this is C, like if there exists x1, x2, so we want to solve following vector equation: x1 a1 plus x2 a2 and x n an equals v. This is vector equation. Or equivalently, you want to solve augmented matrix, so given by those as coefficient matrix and V as the other side. Solve this. So to do that, we need to obtain REF of AB. So REF AB. And then if there is a solution or this is consistent, then we can say yes. So V belongs to column A. So the condition for the consistency of this linear system is last column has no pivot. So let's look at this question. An example. So we have A given by 3 by 1, 2, 3, 4, 5. So 3 by 4, a 3 by 5 matrix. And we want to ask if this vector V belongs to this column A. In other words, we want to solve AV. So at the end, we want to check the last column. If there's no pivot in the last column, then we're done. We can say yes, V is in column A. Otherwise, it's no. So we have this matrix A, and negative 4, 3, 7 is negative 4, 3, 7 goes to the other side of bar. And this is augmented matrix we are going to work on. For this, we try to do REF. So the first ERO we are going to do is I want to swap these two. So R1 and R2. Then this is 1, negative 2, 2, 3, negative 1, 3. And negative 3, 6, negative 1, 1, negative 7, negative 4, 2, negative 4, 5, 8, negative 4, 7. And then we want to kill these two, because this will be the first pivot. This is pivot. So R1 plus, no, 3 times R1 plus R2, replace R2. And I also want to do simultaneously replace R3. Then the first row will be unchanged, and this is 0, 0, 5, 10, negative 10, 5. And the last one is 0, 0, 1, 2, negative 2, 1. So our staircase, suppose this is pivot, first pivot. And then we coming down. So the next pivot will be 5. Or if you want to do a little bit, yes, we can just fix 5 as our pivot, because if you see the second row, this is all multiplication of 5, so we can actually divide by 5 to make this one as 1. And we also need to kill this entry. So to do that, R2 divided by 5, replace R2. 1, negative 2, 2, 3, negative 1, 3, and 0, 0, 1, 2, negative 2, 1. And using this new R2, we can kill R3. So 0, 0, 0, 0, 0, and this is also 0. Now if we make staircase, we have 2 pivots, and there's no pivot in the last column. The answer is yes. So no pivot in the last column. So it's consistent. In other words, V is in column of A. So if we conclude, if you want to solve, if you want to check if a given matrix V is in column A, it is consistent to ask, equivalent to ask, is consistent. Not B, it's V. Null space, the second special space. The null space of matrix A is the set of all solutions of AX equals 0, homogeneous equation. And we use null A to denote this solution set, AX equals 0. And a typical question is find this null space. So to do that, we want to solve this augmented matrix, because this augmented matrix corresponds from here, homogeneous equation, that this 0 goes to the other side of this bar, right hand side of the bar. So we obtain REF after many EROs, and then write the solution in a parametric vector form, so in this way. And then the null spaces are given by span of those vectors in the vector form, PVF. Let's find out, let's look at this example. So given a matrix, the same matrix actually, and from the previous example, I want to find the null space of A. So we go back, so we need to solve A0, so we need REF, because we've already done this REF from this, we came to this REF, so we can start from here. This is REF, and we actually want to solve for augmented matrix we actually want to solve the augmented matrix given by 0, 0, 0 on the right hand side of the line, and this one, so it is the same thing as 0, 0, 0. And this is not ready for REF. This is REF because this entry must be killed to become reduced REF. To do that, we only need to replace R1 by this operation. So the row 2 and row 3s are the same, but row 1 is going to be like this. This is REF because if we put a staircase those are pivot. Those two are pivots, and in the pivot columns, all the remaining entries are just killed to 0. Now, what is PVF? So we write vector form. So we know that this is x1, x2, x3, x4, x5. And we solve for basic variables. Those are basic variables. And other things are free variables. So free variables goes to the other side. So from the row 1, we can write this as x1 minus 2x2 and no x3 minus x4 plus x5 equals 0. And we solve for this, which means x1 is separated out, and the other things are just going to 2x2 plus x4 minus x5. Now from row 2, we can write, because 0, 0 for the first two terms, so this is one thing I will from row 2, I can write x3 plus 2x4 minus 2x5 equals 0, which means this basic variable can be written as x3 equals 2x4, negative 2x4 plus 2x5. And to write vector form, we don't forget free variables, copy it down. Now rearrange this answer, this form, to the vector form. So this is basically concluded to vector form. So x2 coming out for this column. Then we can put the coefficients in order. Empty spots means 0. And x4 this is, so the second term is 0. Negative 2, 1, 0. x5 negative 1, 0, 2, 0, 1. All right. Then the null space is ready to write. The null space are span of these three vectors. And this actually tells us the dimension of null space is 3, which will be discussed in more details.